to talk about this AIDS vaccine trial before we start talking about the course material, but the issues that come up in this are things that we're going to be addressing later on in the semester when we talk about experiments versus observational studies and hypothesis testing. And in particular, there's a tie between this and Fisher's exact test, which we'll talk about in some detail. So there have been a number of articles in the international press, including this one the other day from the New York Times. It's funny, the New York Times apparently called me and sent me email while I was lecturing to you guys. So I got out and had these messages. They wanted comment on this AIDS trial that took place in Thailand. So the story is that this was a massive trial with roughly 16,000 people involved. They were recruited at various centers in Thailand. Some of them were given a placebo. Placebo is something that doesn't have any direct biological effect, might have a psychological effect, but it doesn't have any pharmacological effect directly. And the others were given this mixture of two vaccines. There were two different things involved. Followed people up for some period of time. So that it's not just one vaccine, it's not just two vaccines once, it's a sequence of something like 4 injections, if I'm remembering correctly, over some period of time. And then they look at, during the time of the follow-up, how many people contracted AIDS in each of the two groups, the group that got the vaccines versus the groups that got the placebo. And what they found was that slightly fewer people who got the vaccines got AIDS than people who got the placebo vaccines, the placebo shots. So in particular, the rates of infection among the people who were involved in this trial were relatively high by U.S. standards. I think it was over about a 6-year period, if I'm remembering right, and something like 0.9% of the control group and 0.7% of the treated group got AIDS during that time. So it's just an enormous infection rate compared to how things are in the U.S. I don't know whether that's typical for Thailand overall or whether these centers that recruited subjects were recruiting people who were particularly at high risk. I know that transmission rates in Africa are very high. Transmission rates in Thailand are very high. I don't know whether this is typical or just what happened in the study group. At any rate, they analyzed the data in a number of ways. So if you've got, there were roughly 8,000, I've got the numbers over here. There were 8,200 in the placebo group, and there were 8,202, I think, in the vaccinated group, in the treatment group, and in those two groups, 56 of the people who were vaccinated contracted AIDS, and 76 of those who were in the placebo group contracted AIDS during the trial. So the question is, can you figure out whether that is a surprising difference if the vaccine didn't actually help, right? So it turned out that fewer people who got the vaccine got AIDS than people who got the placebo, but it's going to be one group or the other that gets less, right? It's very kind of not plausible that the two groups would end up with exactly the same number. So the question is the difference between the number of people who contracted AIDS in the two groups surprising if the vaccine really didn't help you at all, if the vaccine made no difference? And one of the big issues is, how strong is the evidence that the vaccine helps? So first of all, how big is the effect? And then how big is the apparent effect? And then secondly, is that apparent effect so big compared to the sample sizes that are involved that you can be really confident that the vaccine helps? Or is that apparent effect small enough compared to the size of the experiment that you can't conclude confidently that the vaccine makes a difference? So if you look at the difference in the raw rates, as I said, it's something like 0.9% versus 0.7%. It's about a 25% difference in rates at which people contract AIDS in the two groups. So roughly a 25% reduction in risk. But it's still a very small number. It's from a small number to a smaller number and yet all the numbers are bigger than they are in the US and the general population. So how do you think about the issue of, is this difference between 56 and 76 surprising or not? Okay. So that's a fundamentally statistical question, and it's the kind of question that we're going to figure out how to answer. How strong is the evidence that the vaccine helps? Right, so you could imagine the following. Each person is represented by, each person in the study, among the 16,402 people, each person has a ticket. And on the ticket are sort of two numbers. One, this represents what's going to happen if the person is vaccinated. This represents what's going to happen if the person is given the placebo. And it might be that this person won't get AIDS if he's vaccinated and won't get AIDS if he's given the placebo. Here's another person represented by the same ticket. This person might not get AIDS if vaccinated, will get AIDS if given the placebo. Here's somebody else who's going to get AIDS no matter what. Okay, does this make sense? All right, so we can think of those numbers as being fixed ahead of time. If the vaccine makes no difference whatsoever to who comes down, who contracts AIDS, then for each person, these two numbers are going to be equal, right? So because if the vaccine doesn't help, I'm either not going to get AIDS no matter what, or I am going to get AIDS no matter what. The vaccine doesn't change anything. That makes sense? So now I can say, let's look at how many people in all contracted AIDS and in the study group, and the answer to that is 56 plus 76, which is what, 132? So I can imagine that I've got this population that I have 16,402 tickets. Of those, 132? 132 of them have a 1 and a 1, and the rest of them have a 0 and a 0. Okay? And now I'm going to take a random sample of those, and I'm going to put, what did I say it was? 8,200 of them got the placebo. So 8,200 of them are going to be labeled placebo, and I'm going to look at the placebo column. And the other 8,202 are going to be the ones who are vaccinated, and I'm going to look at the vaccination column for those people. I get to see one number or the other. But if the vaccine makes no difference, the two numbers are equal for each person. And so it's as if I simply took a random sample from these 16,402 tickets, of which 132 of them had 1s on them and the rest had 0s on them. How surprising would it be if I did that 56 of them would end up in the vaccinated group and 76 of them would end up in the placebo group, right? Whether you're going to get in this little story, whether you're going to contract AIDS or not is sort of predetermined. Whether you get the vaccine makes no difference whatsoever. What's the chance that just because I'm randomly assigning 8,200 of the people to one group and 8,202 to the other group, that I'm going to end up with a disproportionate number in the vaccinated group, disproportionately small? So I can say, well, would I be surprised if the difference between these two groups were this large in either direction? Okay, so just imagine taking these 16,402 tickets, reaching and pulling out 8,200 of them and saying, you guys are the vaccinated group. Did I get that right? No, you guys are the placebo group. Okay, and I do that over and over and over again. And I look at how often the difference between the rate in the vaccinated group and the rate in the placebo group is as big as this or bigger, right? Tells me how surprising it would be to see this if the vaccine makes no difference whatsoever. And the answer is about 8% of the time you would see a difference this big or bigger. Okay? So is 8% a small number? Is 8% a big number? That's kind of hard to say. If you do enough trials, it's pretty, it's pretty nearly guaranteed that eventually, an event that has 8% probability is going to happen, right? I mean, if you did this 100 times, if you did 100 trials of the vaccine, you'd be pretty confident at least one you'd get something that was 8% or less likely to occur, even if the vaccine makes no difference whatsoever. All right, let's look at what the reporter said. So this 31% number is based on a different analysis, which I actually don't trust as much. All right. Okay, so this, with deference to the reporter, this is gibberish. Okay, 16% chance that the results were due to chance. Doesn't make sense. Neither does this 8% chance that the results were meaningless. Okay, I just explained to you what the 8% chance has to do with. What's going on here is assume the vaccine doesn't work. What's the chance you would see as big an effect as you saw? That's the calculation, right? It's not what's the chance that the results are meaningless or what's the chance the vaccine doesn't work. Vaccine either does work or it doesn't work. There's no probability about that. What's the probability? And the probability is in suppose it doesn't work, what's the chance the data would come out the way the data came out? Okay, what's the chance the difference in rates between the control group and the vaccinated group would be the 26% difference that it was, the difference between roughly 0.9% and 0.7%. Right, so it's a very different question, and this has gotten garbled. This make sense to everybody? Okay, all right. The original study is here in the New England Journal of Medicine. It came out in the middle of the night on Monday, and you can click through to read it to get some idea of what they're doing. It's very interesting, very complicated protocol, very complicated procedure, massive undertaking, not a terribly compelling conclusion. I mean, it doesn't mean it doesn't work, but it's just not very strong evidence that it does work, nor does the effect seem to be that large. That doesn't mean it couldn't save a lot of lives. Who knows? Yeah. Exactly. So 8% is the chance that if the vaccine doesn't work, you would see that big a reduction in risk.
What's the complement of that? So 92% is the chance that if the vaccines did work, you would see that big difference?
So the 92% is the chance that you would see a smaller effect than that on the assumption that the vaccine doesn't work. So the calculation is all on the assumption that the vaccine doesn't work. So it's not the probability that it doesn't work, it's assume it doesn't work, what's the chance you see what you saw? Right? That's called a p-value. We'll get there. Other questions about this stuff? Okay, let's go to course stuff. We were talking about, we talked about the definition of conditional probability, we talked about independence, and we talked about the fact that there's a tendency to confuse independence and mutual exclusivity. They're very different. That if you have two events and neither of them has probability 0, if they're mutually exclusive, they're dependent. They can't be independent. All right. We can turn the definition of conditional probability around to make something called the multiplication rule. So if you remember, the definition of conditional probability is the probability of an event A given an event B is the chance that both A and B occur divided by the chance that B occurs if P of B is not 0. Well, there are a lot of situations where it's kind of easier to understand what P of A given B is than to calculate P of the intersection of A and B. And so it's helpful to be able to turn this around and just say if we multiply both sides by P of B, and then flip this over, we've got the probability that A and B both happen is the probability of A given B times the probability of B. And this is called the multiplication rule. Right? All I've done is multiply by P of B. All right, so why is this helpful? Well, very often this is an easy thing to think about. So for example, if I ask, what's the chance that the first two cards in a well-shuffled deck are kings? Okay, the top card and the second card. That's the intersection of two events. The first card is a king and the second card is a king. What's the chance that, let's call A the event that the second card is the king and B the event that the first card is the king, just because that's going to be easier to think about. So what's the chance that the second card is a king given that the first card is a king? You know, well-shuffled deck, you know the top card is a king. What are the options for the second card? There's 51 different possibilities, right? How many of those are kings? 3, okay? And those are all equally likely because all the permutations of the deck were equally likely. We had a uniform distribution on permutations of the deck. So this number is 3 out of 51, right? And what's the chance that the first card is a king, the top card? Unconditional chance the top card's a king. 4 out of 52. Okay, so the chance that the first card is a king and the second card is a king is 3 out of 51 times 4 out of 52. That's an easier way to calculate things than to start thinking about all the ordered pairs you could have in the first two cards. Right? Very often, if you're talking about a test for a disease, some kind of screening, something like that, this is an easy number to come up with. It would be something like, what's the chance that you test positive for steroid use given that you're using steroids? Okay? Does that, so you can calibrate a test that way. You can take a bunch of people who are using steroids and run the test on them and see how often they test positive. Okay? But if you pull somebody at random from a population and you want to know what's the chance that that they sort of have that they are using steroids and test positive for steroids, right? That they test it's a different thing. You've got to think about. Okay, I'm getting a little bit ahead of myself. Let's do an example that involves screening, and I'll go through the one that's. No, actually, let's slow down. Let's do this first. Exercise 14.8. You're taking a statistics class. Grading policy says you have to get a C or better on the homework and the midterm and the final, or get a B or better on the final in order to pass. Okay? And let's suppose that you don't do any work at all. You just guess on everything. Okay? So, and you guess independently on the homework, the midterm, and the final. And let's suppose the chance that you can get a C or better on the homework by guessing is 23%. Chance you get a C or better on the midterm by guessing is 18%. And the chance you get a C or better on the final by guessing is 16%. And finally, the chance you get a B or better on the final by guessing is 5%. Okay? So first of all, can you tell from this what the chance is of getting exactly a C on the final is, rather than a C or better? Forget about plus minus. We're thinking of grade can be C, B, A. Sorry? 13? Okay, so the chance you get a C or better on the final by guessing, is 16%. The chance you get a B or better on the final by guessing is 5%. So it'd be 11%, right? Okay, you've got the event that you get a C or better, a subset of that is the event that you get a B or better, right? So the bigger thing would be C or better, the smaller is B or better. The difference is exactly a C. Yes? Okay, so you've taken the event that you get a C or better, partitioned it into two pieces. You know the probability of this, you know the probability of one of the pieces. What's left over is the probability of exactly a C. So 16% minus 5% is 11%. Okay. What's the chance that you pass the course by guessing? Guess. No. Okay, we have to, there's two ways that you can pass by guessing, right? You can either get a B or better on the final, or you can get a C or better on everything. Yes? Now, those aren't mutually exclusive the way we've said them, yes? Because if you get a C or better on everything, that includes getting a B or better on the final as one possibility. So if we want to divide and conquer, we want to break this up into pieces to find the probability, we're going to want to break it into things we can calculate the probability of separately, right? The easiest thing is going to be to break the event that you pass the course into disjoint events, each of which we can find the probability of. So we can sum the probabilities to find the overall probability. So what are the two sort of disjoint ways of passing the course by guessing? Yeah.
Getting C or better on the homework in midterm, getting C on final, or getting B or better on.
Excellent. Okay, so one way to pass the class is you get a C or better on the homework, C or better on the midterm, and exactly a C on the final. Right? And another way is to get a B or better on the final, regardless of what your homework and midterm are. Now, those two ways of doing it are now disjoint, right? Because if you get a B or better on the final, you didn't get exactly a C on the final. So now we can find the probability that you pass the class by finding the probability of those two disjoint ways of doing it and adding their probabilities. So the first event we'll call A is the event that you get greater than or equal to C on homework, greater than or equal to C on midterm, and exactly a C on the final. If the chalk is particularly fragile or I'm particularly brutal on it today, but greater than or equal to B on the final. Okay, and now A intersect B is empty, they're disjoint, and A union B is all the ways that you can pass the class. Okay, so we've partitioned the event passing the class into two disjoint pieces. We can find their probabilities separately and add them to find the probability that we pass. Okay? So how about this one? The probability of that ought to be pretty easy. Yeah, it's given. It's 5%. Okay? So P of B is 5%. And what's P of A? Well, this has to happen, and this has to happen, and this has to happen, right? It's the probability of an intersection. One of the assumptions is that you're guessing independently on all these things. So the event that you get at least a C on the homework is independent of the event that you get at least a C on the midterm, and that's independent of the event that you get exactly a C on the final. So we can find the probability that this happens, and this happens, and this happens by multiplying the probabilities that they happen separately using the independence. Okay? So what's the chance you get at least a C on the homework? So that's 23%. What's the chance you get at least a C on the midterm? 18%. And what's the chance you get exactly a C on the final? Figure that that was 11%. Okay, so the probability of A using the independence is, what did we just say? It was 0.23 times 0.18 times 0.11. Okay? And so if we add 0.05 to this product, that's the chance you pass the course by guessing. Is all right? Any questions? Good? Okay. So we used independence to find the probability of intersection. We first broke things up into disjoint pieces so we could add their probabilities to find the probability that either of those things occurs. Okay. Let's talk about screening for a disease or a condition or something like that. All right, so let's suppose that 10% of some population has benign chronic flatulence. Yes?
Just real quick back to that one. What's a good way of remembering the 23, 18, or 11 were independent, and you multiply those, and then you add the probability of BFA, you know they're independent also. So how do you remember which when you multiply and you add?
Okay, so when do you multiply? When do you add? Okay, if you want probability of A union B and A intersect B is disjoint, they're mutually exclusive, then you can take P of A union B is P of A plus P of B. Okay, and that's one of the axioms, right? That's just got to be true. So if you're looking for the probability of the union and the events are disjoint, you can find that probability by adding. If you want probability of A intersect B and A and B are independent, you can find it by multiplying. P of AB is equal to P of A times P of B. And that's sort of the definition of independence. Okay. If you're looking for the probability of the union and the events aren't mutually exclusive, you can't just add. You got to subtract off the probability of the intersection. If you're looking for the probability of the intersection and the events aren't independent, you can't just multiply. You got to do something else. You could use the multiplication rule, because it's always the case that P of AB, it's always the case that P of AB is equal to P of A given B, P of B. Just in the special case of independence, P of A given B is P of A. Learning that B happened doesn't tell you anything about whether A happened. It's the same as the unconditional probability. Over here, it's always the case that P of A union B is equal to P of A plus P of B minus P of A intersect B. In the special case that their intersection is empty, that probability is 0. So it reduces to this. We good? Okay, people have had a chance to... Okay, so suppose we have a way of screening for benign chronic flatulence that has a 90% chance of correctly detecting that you have this condition, which is not fatal, and a 10% chance of a false positive. Okay, so there's a 10% chance that the dog did it or something. Okay, and you pick a person at random from the population, so everybody has the same chance of being picked, and you test the person, and the test reports positive. What's the chance the person actually has the disease? So I don't think I said out loud that we've got 10% of the population has the condition. The test is 90% accurate. Somebody tests positive. What's the chance they actually have the disease? Now, this is an invitation to make them. People's intuition very often leads them astray in this particular thing. Think, oh, if the screen is 90% accurate, then if somebody tests positive, there's a 90% chance they have the disease. Right? Wrong. Yep. What does the 90% say? It's 90% chance that you test positive if you have the disease, not 90% chance that you have the disease if you test positive. It's the other way around. Okay? So what we need to do is turn the conditional probability of testing positive given that you have the disease into the conditional probability that you have the disease given that you test positive. They're two different things, two different conditional probabilities. One is probability of A given B, the other is probability of B given A. Right? Okay, well let's use D to denote the event that the person has the disease, T to denote the event that the person tests positive. So translating the words into symbols is the hard part of most of these problems. Once you've got it translated into math, then the math isn't very difficult. Right, so what the problem statement said is that 10% of the population has the disease, so the probability that a person picked at random from the population has the disease is 10%. P of D is 10%. And the test has a 90% accuracy, is interpreted to mean the chance that you test positive given that you have the disease is 90%. The chance that you test positive if you don't have the disease is 10%. Those are two different pieces of information. You can't derive this from this. Right? The numbers are happening to be the complement because we're saying that the test is sort of 90% accurate in both directions. The chance of a false positive is 10%. The chance of a false negative is 10%. Does that make sense? Okay. All right. So what we're supposed to find is what's the chance that the person has the disease given that they test positive. What we're given is what's the chance they test positive given they have the disease, the other way around. Okay? So by the definition of conditional probability, that is simply the chance that they have the disease and test positive divided by the chance that they test positive. Now, problems like this that start involving conditional probabilities, the easiest thing to do to solve them is to draw a tree. If you draw a tree, you will seldom go astray. I need to put more trees in the book, but I haven't done it yet. All right, so the population is divided into two groups, those who have the disease and those who don't, right? Now, there's a 10% chance that a person picked at random has the disease, a 90% chance that a person picked at random doesn't. So this is D, this is D complement. Then, if you have the disease, there is a 90% chance that you test positive for it, and a 10% chance that you test negative. If you don't have the disease, there's a 10% chance that you test positive and a 90% chance that you test negative. What we're putting here are conditional probabilities. So what is the probability that somebody is in this group? That is, has the disease, tests positive. Multiplication rule says the chance of D intersect T, the chance you have the disease and test positive, is the conditional probability that you test positive given that you have the disease, that's 90%, times the unconditional probability that you have the disease, that's 10%. So the amount of probability that's down here, this node, which is has the disease and tests positive, has probability 0.9 times 0.1, which is 0.09. Right, 9%. Okay, these people have the disease and test positive. 9% chance of that happening if you pull a person at random and test them. Right? This is has the disease, test negative. Right? 10% is conditional probability that you test negative given that you have the disease. 10% is probability you have the disease. So probability that you have the disease and test negative is this conditional probability times that unconditional probability. 0.1 times 0.1 is 0.01, 1%. Yes? So this is 1%, and that is dt complement. Then here, this is don't have the disease, test positive. Probability of that intersection is this conditional probability times that unconditional probability. 0.1 times 0.9 is 0.099%. So this here is 9%, and that event is D complement T. And then this pile here, probability that you don't have the disease and test negative is the conditional probability that you test negative given that you don't have the disease times the unconditional probability that you don't have the disease. We have 0.9 times 0.9 is 81%. Yes? And that is D complement T complement. And just as a sanity check, do these add up to 100%? Yep. 81 and 9 is 90 and 10 is 100. Yeah? Okay. So this is a good thing. All right, so what are we interested in? We're interested in the probability that you have the disease given that you test positive. So which of these branches of the tree corresponds to testing positive? The ones that have a T in them, yeah? Not a T complement? So that's this, and I think I'll draw that to include the probability, that, and that. Yes? Okay, so when we condition on the event that the person tests positive, we're limiting the universe to these outcomes where somebody tests positive. Of those, what fraction actually have the disease? It's 50%, right? It's 9% divided by the 18%. 18% of people are going to test positive. Of those, half, 9%, actually have the disease. The other half are false positives. This make sense? Okay, so what we've got is probability that you have the disease given that you test positive is probability that you have the disease and test positive divided by the probability that you test positive. We have partitioned the event that you test positive into two pieces. You can test positive two ways. You can test positive and have the disease, or test positive and not have the disease. Those are the only possibilities, right? So this denominator is, the numerator is still P of dt. The denominator is P of dt plus P of D complement T. Right? We've partitioned the event T into two disjoint pieces. T and D, T and not D. Yep. And what we just did, this is equal to 9% over 9% plus 9%. And that's a half, right? Okay, so even though the disease is even though the test is 90% accurate, the conditional probability that you have the disease, given that you test positive, is only 50%. Okay? Because a lot of the positive test results are false positive test results. Okay? So you need to take the base rate of occurrence of the, in this case, the disease, into account in figuring out what the chance is that a person has the condition given that they test positive for the condition. The base rate matters. Okay. All right. Now, the way we actually did this, you can kind of work out, we calculated this. We calculated this by using conditional probability times unconditional probability to find the probability of this piece. We partitioned this event into two disjoint events. For each of those, we found their probability by multiplying a conditional probability times an unconditional probability. We can write down what we did in symbols, and that's called Bayes' rule. So let's look at what we actually did. Right, we said P of dt, P of d given t is P of dt divided by P of dt plus, P of t. And that's P of dt over P of dt plus P of d complement t. Right? That's partitioning the denominator into two pieces. Now, how did we actually calculate that? We calculated that as probability t given d, P of d. That's how we calculated the numerator, P of dt. We took P of t given d, 90%, times the unconditional probability of d, 10%. How did we calculate these bottom pieces? Well, it was P of, this piece is the same as the numerator. That's t given d, P of d, plus P of t given d complement, P of d complement. So we used the multiplication rule to calculate the numerator and to calculate the two pieces of the denominator. Right? This is called Bayes' rule. The Reverend Thomas Bayes. Okay. Bayes' rule is a way of turning a conditional probability into sort of the converse conditional probabilities. It's expressing P of d given t in terms of P of t given d and P of t given d complement. Okay? Memorizing the formula will probably not help you. Being able to derive the formula will help you. Being able to draw a tree will definitely help you. Okay, so if you get a problem like this, drawing a tree is the way to go. You're much less likely to get confused about what goes where. Yes?
So for the tree, like the first top branches, you know that the way you drew was 10% have disease and then 10% don't have disease.
Right.
So how do you know that the top branches wouldn't be the test is positive 90% and then the other one is it's negative 10%? How do you know the order of?
Okay, so the question is how did I know to sort of start by branching on who has the disease and who doesn't have versus branching on who tests positive and who doesn't test positive? Well, the answer is this is people, right? And I'm dividing people into groups. I don't know how many people test positive. That's actually not given. That's kind of what I'm trying to figure out. I do know how many people have the disease. That is part of the problem statement. So I actually don't even have the information I would need to branch on test results first. Does that make sense? Yep. Okay. Other questions? Okay. There is an example I would encourage you to work through for fun. It's this 14.7, but I just have to talk about it briefly, although I'm not going to go through it. So it's been said that if you put enough monkeys in front of typewriters and you wait long enough, one of them will type the complete works of Shakespeare. My colleague Robert Walensky in the computer science department said the following. We've all heard that 1 million monkeys banging on 1 million typewriters will eventually reproduce the entire works of Shakespeare. Now, thanks to the internet, we know this is not true. Anyway. This is an interesting problem. It's worth puzzling over for a little bit. I want to go on and talk about the next chapter, but let's do one slightly more complicated problem first. We toss a coin 5 times independently, and the question is, what's the chance the total number of heads in the first 3 tosses is less than or equal to the total number of heads in the last 2 tosses? How on earth do we figure this out? We could start by naming things, right? It's always a good idea. Introduce some symbols. Give things a name. All right, so let's let x be the number of heads in the first 3 tosses. And let's let y be the number of heads in the last 2. So what we're asking is, what's the probability that x is less than or equal to y? Okay? So that's some event. What are the possibilities for x and y? What can they each be? How many heads can you get in 3 tosses of a coin? 0, 1, 2, or 3, right? Okay, the possible values are 0, 1, 2, and 3. What are the possible values here? 0, 1, and 2. Okay. What combinations of values correspond to x being less than or equal to y? All right, so any of those, there's 4 possibilities for the first and 3 possibilities for the second. There's 12 possibilities in all, right? They're not equally likely, but there are 12 possibilities. Some of them correspond to x being less than or equal to y. Some of them don't. So for example, if x is 2 and y is 0, x is not less than or equal to y. Okay. If x is 0, y can be anything, and x is less than or equal to y. Yes? Okay, so let's just make a little table, x, and then what are the possible values of y that corresponds to x being less than or equal to y. So if x is 0, y can be 0, 1, or 2, and x is in fact less than or equal to y. Yes? If x is 1, y can just be 1 or 2 in order to have x less than or equal to y. If x is 2, y can only be 2, or else x is not less than or equal to y. And if x is 3, y can't be bigger. Yep. So these are the outcomes that correspond to the event that x is less than or equal to y. So far, so good? Okay. Are these mutually exclusive? If x is equal to 0, x is not equal to 1. Right? These rows, if you like, are mutually exclusive. Yeah? Okay. So if I can find the probability of any of these 3 things happening, right? This is really 3 outcomes. It's 0, 0, 0, 1, 0, 2. Right? And this is 2 outcomes, 1, 1, and 1, 2. If I can find the probability of any of these 3 things happening, I can add it to the probability of either of these 2 things happening and add it to the probability of this happening. And what I've got is the probability that x is less than or equal to y. Okay? So how do I find this? Well, what's the chance that x is in fact... So now I want to now divide this up in another way. What's the chance that x is 0 and y is 0? It's the intersection of 2 things. Chance x is 0, the intersection of the event that x is 0 and the event that y is 0. the number of tosses and the number of heads in the first 3 tosses is independent of the number of heads in the second 2 tosses, right, in the last 2 tosses. Yes? So the event that x is 0 is independent of the event that y is 0. So I can find the probability that x is 0 and y is 0 by multiplying the chance that x is 0 times the chance that y is 0, using the independence. Yes? Okay. What's the chance that y is 0, 1, or 2? Sorry? 1, yeah? Those are the only possibilities for y. Okay. What's the chance that x is 0? Toss a coin 3 times. 50% chance, it's a fair coin, tosses are independent, 50% chance that it lands heads the first time, 50% chance it lands heads the second time, 50% chance it lands heads the third time. In order for x to be 0, it has to land tails all 3 times. Okay? So the tosses are independent. So the chance it lands tails the first time and the second time and the third time is the chance it lands tails the first time times the chance it lands tails the second time times the chance it lands tails the third time. That's the independence in action. Right? So we have a half times a half times a half. It's an eighth. Good? So the chance that x equals 0 is an eighth. I'm not sure how to do this clearly. I guess I'll put the probabilities here. So the chance of that is an eighth. And what's the chance that y is 0, 1, or 2? We just said it's 1. So the chance that x is 0 and y is 0, 1, or 2, because x and y are independent, I can just multiply. That's an eighth times 1, and the whole contribution of this is an eighth. What's the chance that x is 1? So this is a probability, this is a probability, this is a value. Okay, how can x be 1? I need to get 1 head and 2 tails. Yes? That 1 head could be on the first toss, or the second toss, or the third toss. That's a partition, right? Because if it's on exactly the first toss, it wasn't on the second toss. If it's on the second toss, it wasn't on the third toss, et cetera. Okay. So what's the chance that I get a head on the first toss and then 2 tails? That's an eighth, right? A half times a half times a half. What's the chance that I get tails on the first toss, heads on the second, tails on the third? Half times a half times a half is an eighth. What's the chance I get 2 tails and then a head? Half times a half times a half is an eighth. Yes? There's 3 disjoint ways that I could get 1 head and 2 tails. Each of them has probability an eighth. So the chance that I get exactly 1 head in those 3 tosses is 3/8. Yes? What's the chance that I get 1 or 2 heads in the last 2 tosses? Well, it's the chance of anything minus the chance that I don't get any heads at all. Right? You find probably the complement is easier in this case. The complement of the event that I get 1 or 2 heads is the event that I get no heads at all. Yes? Because those are the only possibilities here. What's the chance I get no heads at all in the last 2 tosses? Quarter, right? Tails, tails, a half, quarter. So the chance that I get either 1 or 2 heads is 3/4. Yep, 1 minus a quarter, so this is 3/4. And the overall chance that this row happens, that x is equal to 1 and y is equal to 1 or 2, is 3/8 times 3/4 because x and y are independent. So 9/32. What about here? What's the chance that x is equal to 2? I need to get 2 heads and 1 tail in the first 3 tosses. Those could be heads, heads, tails, heads, tails, heads, tails, heads, heads. Right? I have 3 choices for which one gets tails. Just like here, I had 3 choices for which one gets heads. Same probability, 3/8. What's the chance y is equal to 2? Quarter. Okay, so this is 3/8 times a quarter by independence, which is 3/32. Okay, 1/8 is 4/32. So I've got 4 plus 9 is 13 plus 3 is 16 over 32 is a half. Okay, so overall, this whole probability is a half. Everybody follow all the moves? We used independence a lot. Used independence of all the tosses. We used the complement rule to find the chance of getting either 1 or 2 heads by subtracting the chance of getting no heads from the chance of getting 0, 1, or 2. Okay. Speak now. All right. Again, we have kind of blasted through, but I'd like to do this. Anybody looked at this chapter yet? Chapter 15? Let's make a deal problem? Anybody heard of the let's make a deal problem or the Monty Hall problem? Yeah, there was a game show called Let's Make a Deal. And one of the things that happens in the game is that there are 3 doors, one of which hides a brand new Corvette, and one of them hides a goat, and the other one has a year's supply of hay for the goat, or something like that. So there's a prize that you want, and then a couple of things that are jokes. Okay? And what happens is you're offered a chance to pick a door, and after you've picked the door, the host, Monty Hall, shows you that the prize you want is not behind one of the doors you didn't pick. Okay, so you pick door A, and the host shows you that door B has the year's supply of hay. And the question now is it better strategy to stick with your original guess or to switch your guess to door C? He offers you now a chance to switch. He shows you that the grand prize is not behind a door you didn't pick and offers you a chance to switch. Should you switch? No, yes, yes, no, yes, no, maybe. Who cares? Who wants a Corvette anyway? Yeah. Okay, so what makes this more entertaining is that this question was posed to Marilyn Vos Savant, the world's smartest human. The Ask Marilyn column, I don't know, is she still an active column? Yeah, okay. So, and she said that you should switch. And a handful of university professors wrote back to her saying, you're wrong, here's the math, you shouldn't switch. Conditional probability that the prize is behind door C, given that it isn't behind door B, is 50%. And so you're wrong, Marilyn. All right, so the question is, who's smarter, Marilyn or the professors? So here's a model of the game. So Monty offers me a chance to pick a door. I pick door A. Monty shows me that the prize is not behind door B. Now I have a chance to switch. Should I stick with my original guess or pick door C? I'm going to stick with my original guess. Oops, it was actually behind door C. I would have lost. Okay, so again, I pick door A. Monty shows me it isn't behind door C. I'm going to pick door B. Oh, I won. Okay, proof. No. We're actually going to look at doing this over and over again and figure out what the probabilities are that you would win a certain number of times with a particular strategy in repeated play, and see if we can use that to figure out empirically what the right answer is. But first, we're going to work on it theoretically. Yes?
Would you say, or would you pick a different number?
We'll get there in excruciating detail. All right, so I picked door A. He showed me it isn't behind door B. I stick with my original guess. I lost. Okay, these are, by the way, this really is being done as randomly as I can do it with a computer, right? The computer is hiding the prize behind a door at random, and after I click, it is showing me a door that the prize is not behind, and it's not then moving the prize, right? It's sort of the prize is staying where it was, and I get to pick another door. So I'm going to stick with A again. Oh, that time I won by sticking with door A. Okay? All right. So what's the better strategy? All right. So what are the rules of the game? So we're going to assume the prize is hidden at random. There's a chance of a third of it being behind each of the three doors. I'm going to pick a door at random. It really doesn't, if the prize is hidden at random, it sort of doesn't matter how I pick. But the point is that I don't have any information about what door hides the prize. So I'm not able to sort of exploit something to do a better job at that stage. Then an important rule is that the host is never going to open a door and say, there's the Corvette, you didn't get it, right? Not until after the next round, right? The door he opens is always going to be a door that doesn't have the prize behind it. Okay? So far, so good? All right. So here is the naive argument. So don't switch, because after the host shows you what's behind one door, there's two doors left. The prize is equally likely to be behind either one. There's no advantage to switching. Doesn't matter whether you switch or not. Okay? Now, it was true when the game started that the prize was equally likely to be behind any of the three doors. The question is, when you rule out a door, is it now equally likely to be behind the two remaining doors or not? Okay, this argument says it is. All right. So here's a more sophisticated argument, which is kind of what the professors were saying. So let's call the three doors A, B, and C. Capital A is the event that the prize is actually behind door little a. Capital B is the event that it's actually behind door little b, and so on. So the event B complement is the event that the prize isn't actually behind door B. Okay? That is, it's actually behind either door A or door C. Now, let's suppose I pick door A. The host then shows me that it isn't behind door B. What's now the probability, the conditional probability that it's behind door A versus behind door C? So the calculation would be, what's the probability that it's behind door C given that it isn't behind door B? Well, that's the chance that it's behind door C and not behind door B, divided by the chance that it's not behind door B. This is just the definition, right? But in order for it to be behind door C, it can't be behind door B. So the intersection of C and B complement is just C. C is a subset of B complement. That make sense? It's behind door C. It wasn't behind door B. You already know that. All right, so this is just P of C divided by P of B complement. P of C, that's the chance the prize was originally behind door C. That's a third. The chance that it wasn't originally behind door B is 2/3. Right? So that conditional probability is a half. Okay? And similarly, if you find the chance that it's behind door A, given that it isn't behind door C, you get exactly the same number. It's a half. So according to this argument, there's no advantage to switching. That's what the professors claimed. Right? It's math. It's got to be right. Yeah? Unless it isn't. Here's Marilyn's argument, basically. Suppose you play over and over again. In the long run, a third of the time, your first guess is going to be right. Right? Because long run, a third of the whatever. Say you always pick door A. A third of the time, it'll really be behind door A. And so if you stick with your original guess, you'll win a third of the time. What happens the other 2/3 of the time? Right? The other 2/3 of the time, it's behind one of the remaining doors, but the host shows you which one it isn't behind. And so that other 2/3 of the time, if you switch, you'll win. Right? Does that make sense? 2/3 of the time, it's behind one of the doors you didn't pick. When that happens, if you switch, you win. 1/3 of the time, it's behind the door you did pick. When that happens, if you stick with your original guess, you win. Okay? So divide the universe of possibilities up into two things. It's behind your original guess or it isn't. The chance it's behind your original guess is a third. The chance it isn't is 2/3. If you always stick with your original guess, you win a third of the time, because a third of the time your original guess was right. If you always switch, you win 2/3 of the time, because 2/3 of the time it's behind one of the other two doors, and the host has showed you the one that isn't behind. The only one left is the one that it is behind. That make sense? Okay. So what's wrong with the math? How can the math be wrong? It calculates the wrong thing, okay? There's no algebraic error, there's a conceptual error. The right story, the right thing to calculate is not the probability that it's behind door C given that it isn't behind door B. That's not an accurate description of what happened. It's what's the probability that it's behind door C given that you picked door A and the host revealed to you that it isn't behind door B, right? The fact that you picked door A, the host knew which door you picked, and then using that information decided which door to show you, which door to open. That essential ingredient is missing. The professors calculated the wrong conditional probability, okay? So let's see if we can now work through the right calculation. So what's the chance that it's behind door C given that you pick door A and the host reveals that it isn't behind door B? A little more complicated thing to think about. Well, we're going to divide the universe of possibilities. So under what circumstances, okay, if I pick, I need an extra assumption here, which is what happens if I pick a door that doesn't hide the prize? Which door is the host then going to show me? And we're going to pretend that if I pick door A and it really is behind door A, then the host tosses a coin to decide whether to show me door B or door C, right? If I pick door A and the prize really is behind door B, the host doesn't have a choice. He has to open door C. If I pick A and it's really behind C, he has to show me B. He doesn't have a choice. That make sense? But if I pick door A and it really is behind door A, he has a choice. I'm going to pretend he tosses a coin to make that choice. All right, so we're now going to use the idea that the door that I pick is independent of the door that it's actually behind. I don't have any information to help inform my original choice. So what's the chance that that it actually is behind door C and I pick door A? Well, my pick is independent of how the prize was hidden. So the probability that it is actually behind door C is a third. The probability that I pick door A is a third under the assumption that I'm making. The probability of both of these events, they're independent, so it's the product of their probabilities, that's a ninth. Okay? So far, so good? All right. So now I want to think about what's the probability that I pick A and the host shows me that it isn't behind door B. Well, there's two ways that the host can end up showing me that it isn't behind door B. Right? One way is I pick A, it's actually behind door C. Host doesn't have a choice, has to show me door B. Yes? The other way is I pick A, it really is behind A. Host tosses a coin. 50% chance the host then shows me that it isn't behind B. 50% chance he shows me it isn't behind C. So far, so good? All right, so if I pick A, okay, so I'm partitioning the event that I pick A and the host reveals that it isn't behind B into two disjoint events, right? They're disjoint because if it really is behind A, it isn't behind B or C. That's what I'm partitioning. So chance that it is behind A and I pick A and the host shows me that it isn't behind B, plus the chance that it really is behind C, and I pick A, and the host shows me that it isn't behind B. So what's the chance of this? if it's behind A, what's the chance? So the chance that it's behind A and I pick A, we already figured out as a ninth, right? Okay. If it's behind A and I pick A, half the time the host is going to show me that it isn't behind B, half the time the host is going to show me that it isn't behind C. Right? So this probability is half of a ninth. Okay. What about this? If it's actually behind C and I pick A, chance of that is a ninth, right? But the host then doesn't have a choice. If these two things happen, the host has to show me that it isn't behind B. Has no choice. So the probability of this piece is a ninth. So I have an 18th plus a ninth. Does that make sense? All right. Okay, so now I have all the pieces that I need to do this calculation. What's the chance that it really is behind door C, given that I pick A and the host reveals that it isn't behind B? Well, that's the chance that it is behind C and I pick A and the host reveals that it isn't behind B, divided by the chance that I pick A and the host reveals that it isn't behind B. The chance of this is this thing we just figured out. That's an 18th. I'm sorry. Yeah, that's a ninth. And this other piece is a ninth and an 18th. So we have a ninth divided by a ninth plus an 18th. It's 2/3. Sorry? I'm finding a conditional probability. So the conditional probability of C given this and this is the probability of C and this divided by the probability of this. Okay. So this agrees with Maryland's solution. It says that switching is the better strategy. If I switch, the chance I win is 2/3. If I stick with my original guess, the chance I win is 1/3. Okay. So the problem is not in the arithmetic. The problem is in what is the conditional probability you were trying to compute. The problem is in the conception. Does this make sense? If not, this is a good time to ask questions. Yes?
So, can you go up all the way to argument 4? So the very first line where inside the bracket you have pick A and host reveals B complement. So inside the bracket, shouldn't the host reveals B complement given that you pick A? Like, I mean, if you choose B, then the host wouldn't reveal what's behind B. So shouldn't you pick A happen first and then host reveals B complement?
Okay, so the question is, should this be probability that it's behind door C given host reveals B complement given, okay, so the scenario at the time that you're offered the choice, what has happened? You've picked door A and the host has shown you that it isn't behind door B. That's the information. The information is you picked a given door, host knows that you picked that door. On that basis, host then opens some other door. Okay, so the information that you really have is this, and you get to base your decision on all that information. I don't know if that makes sense or not. You're conditioning on everything that's already happened at the point that you have to make the decision. So you picked a particular door. Host knows you picked that door. Host followed some rules to decide then what door to show you. In particular, the rule is if there's only one door he can show you without showing you the prize, he shows you that one. And if there's two doors he can show you, he tosses a coin. So he's done all that. And now, what should you do? You're not happy, but yeah.
No, but you just said the host first have to know that you picked A.
Right?
So, I mean, isn't that host reveals B complement given you pick A?
No.
Because you said the host has to know that
Okay, so there's a couple of things going on here. I'm going to try to tease them apart. All right, so we don't have a notion of an event given another event. We have a notion of a conditional probability given another event. So what is the event that's being conditioned on? Right, so that we don't have a notion of probability of A given B given C. That's not something we have a definition for, right? It's what we have is chance of A given something, all right? And sort of what's the something that's going to go in here? It's the information that we have about the state of the world. Now, the host decides to reveal B after knowing that you picked A. That's certainly true, right? But the way the host goes about making that decision, we sort of encapsulated in the rules, right? We're using the way the host makes the decision in doing these probability calculations, right? But what we're conditioning on is, where are we in the game? Well, what's happened at this point is I've picked door A, host has showed me it isn't behind door B. That's where we are. I'm not. Yeah, I can tell I'm not satisfying you. I don't have a better way to say it right now, but I'll think about it. Yeah. Okay. No, sorry. Other questions? All right. So, what's wrong here? The first argument just says, oh, if there's two possibilities, they must be equally likely. Well, they're not equally likely. There's no reason to think they're equally likely. In fact, the possibility that it's behind the door you picked is 1/3. The possibility that it's behind the remaining door that's still closed after the host has shown you one is 2/3. They're not equally likely. You can't just assume that they are. Argument 2 does a calculation that is algebraically correct. It's just the algebraically correct calculation of the wrong quantity. It doesn't actually describe how the game is played. Okay. Argument 3 is nice and simple, and it only depends on the assumption that the prize is initially equally likely to be behind any of the 3 doors. Okay. So it's clean. I like it a lot. Argument 4 is more technical. It involves additional assumptions about independence of this and that, and how the host decides which door to show you, so forth and so on. But it gets the same answer ultimately as argument 3. All right, let's work one of these examples quickly. Okay, I'll give you guys a choice. We have 5 minutes. Okay. One is, let's make a deal with the prize behind one of 5 doors. And one is, the host follows a different rule in deciding which door to show you. He doesn't always show you a door that you didn't pick, a door that doesn't hide the prize. Sometimes he just picks at random from the remaining doors. Okay. And this one, the host might even open the door that you picked. Sometimes he's just picking at random completely, including possibly opening the door that you picked. Sorry? So, oh yeah, it does take away the point of the game. Not such a fun game. And then this last one is a completely different thing about mice running in mazes at random mice. Any preference?
Is the thinking behind Mickey Mouse different from the one from the movie?
Let's do the mice. And I'll okay. So you got 2 mice in separate mazes. There's only one path that leads to the cheese. The first maze has 4 paths. 3 of them are dead ends. Second maze has 5 paths. 4 of them are dead ends. The mice go at the same speed. All 9 of the paths are the same length. Each mouse decides at random which path to take first, equal chance of taking each path. If it goes to a dead end, the mouse goes back to the starting point at the same speed, picks one of the remaining paths at random, then same chance of taking each of the untrodden paths. Keeps going until each mouse finds the cheese. The mice are independent of each other. And the question is, what's the chance that the mouse in the first maze takes less time to find the cheese than the mouse in the second maze? Okay. Does this sound at all like a problem we already solved today? No. Because that problem was about coins. That's completely different from random mice. Yeah. This is a lot like the chance that the number of heads in the first 3 tosses is less than or equal to the number of chances in the number of heads in the last 2 tosses. Yes? Okay. What's the chance that, so what are the possibilities? How does the first mouse win? Well, first mouse can take 1, 2, 3, or all 4 paths before finding the cheese, right? So there's 4 possibilities. First mouse can take 1, 2, 3, or 4. Second mouse can take 1, 2, 3, 4, or 5, right? What's the chance the first mouse takes less paths? Well, if the second mouse takes 1 path, the first mouse can't take less. Okay? If the second mouse takes 2 paths, then if the first mouse takes 1, he wins. If the second mouse takes 3, the first one takes 1 or 2, he wins, etc., right? So the outcomes that correspond to the first mouse winning are 1 from here, 2 from here, 1 or 2 from here, 3 from here, 1, 2, or 3 from here, 4 from there, 1, 2, 3, and that, or 4, and 5 from there. Yes? Those are the outcomes that correspond to the first mouse taking less time. The mice are independent. The chance the first mouse takes 1 path to find the cheese is what? What's the chance that, so there's 4 paths to pick from. What's the chance it's the first path the mouse picks? Mouth pick. 1/4, okay? What's the chance that the second mouse takes exactly 2 paths? So the chance of this is 1/4. What's the chance that the second mouse takes exactly 2? For that to happen, the first guess of this mouse has to be wrong, and then the second guess has to be right. Yes? What's the chance that the first guess is wrong? Okay, 4/5. And then if the first guess is wrong, what's the chance the second guess is right? 1/4, right? There's still 1 right path left. There's 4 paths remaining. The mouse is picking equally likely, each one with equal probability. So the chance that this takes exactly 2 paths is 4/5 times 1/4. Okay? What about this? Chance that it takes 1 or 2? Well, chance it takes exactly 1 is 1/4. Chance it takes exactly 2 is 3/4 times 1/3, right? Okay, so 1/4 plus 3/4 times 1/3 is this one taking 1 or 2. What's the chance this mouse takes exactly 3? Well, he's got to be wrong the first time, be wrong the second time, and be right the third time. Yep. Okay. All right, so this is basically the story. And then to find the chance that this happens and this happens, we take this chance times this chance. We've partitioned everything. We add the results to get the overall probability. OK. Yes?
So we're going to take the probability of all this column times probability.
No, in each row, we're going to multiply this times this
I have a new column?
to get a new column, because that's the chance that this happens and this happens. OK, but this corresponds to one way that the first mouse can win. This is a disjoint way that the first mouse can win. This is a disjoint way that the first mouse can win. So we're going to add those probabilities. OK.